In this module, we'll cover partial fraction expansion. In our 7 steps for controller design, the skill of partial fraction expansion is needed to complete step 6. In week 1, we saw many dynamic problems from electrical engineering, mechanical engineering, and aerospace engineering result in linear differential equations. And while we have the mathematical methods for solving these analytically or using differential equation solvers like MATLAB's ODE 4.5, there's an inherent benefit to applying Laplace transforms to these dynamic problems. In the next module, we'll see how engineering systems have many elements or blocks associated with them. In addition to the main system called the plant, there are actuators, sensors, filters, subsystems, and the main objective of this course, controllers. Each of these blocks are themselves dynamic systems governed by differential equations. It quickly becomes impractical to work with these blocks as differential equations, as the output dynamics of one block become the dynamic input to another block or multiple blocks. The primary benefit of modeling with Laplace transforms is we change the analysis from differential equations to algebraic equations. Each block, if linear, results in a ratio of polynomials in the Laplace variable s. Each block is then defined by a lettered function, for example, capital F of s, and that function is called a transfer function. Of course, any capital letter can be used like G or H. Many times subscripts are also used like f sub 1 and f sub 2. Regardless, the transfer function will have a numerator polynomial of degree m and a denominator polynomial of degree n. The transfer function is considered improper if m is greater than n. It is considered proper if n is equal to m or n is greater than m. If n is strictly greater than m, we say it's strictly proper. As we multiply or add blocks in our models, the associated polynomial functions are simply multiplied or added together. We did this in high school using the FOIL method, first, outer, inner, last. In this course, we will let the computer handle that. After all, the degrees of some of these polynomials can be 4, 5, 6, or higher. Doing the FOIL by hand would take hours. You'll be given this Laplace transform table on exams. It contains time-based functions defined by lowercase letters, little f on this table, along with the associated Laplace functions in the variable s. If you scan the Laplace functions, you'll notice most are second degree and a couple are third degree. You won't really see the nice m or nth degree polynomials defined on the previous slide. So now what? That's where the skill or technique of partial fraction expansion comes into play. It can also be called partial fraction decomposition. And there's 3 cases we'll examine in this course. Case 1 involves strictly proper transfer functions with real, non-repeating roots in the denominator. Physically, it means the number of x-axis crossings matches the degree of the denominator polynomial. Case 2 involves strictly proper transfer function with some complex roots. Physically, it means the number of x-axis crossings is less than the degree of the polynomial. The complex roots don't have x-axis crossings. Case 3 involves strictly proper transfer functions with real repeating roots. Physically, it means we get some bounces off the x-axis or some twists through the x-axis. Case 1 is the only case you'll be tested on for an exam. From algebra, we know any polynomial can be factored. We have the quadratic formula for second degree polynomials, and there's closed form equations for third degree polynomials. Anything higher, we really need a computer. Regardless, there's only two types of roots that result: real roots or complex conjugate pairs. And make sure you're absolutely clear on the difference between a factor and a root. Let's walk through an example for case 1, the strictly proper transfer function with real, non-repeating roots. The transfer function f of s is not on the table as written. We can factor the third-degree polynomial into three factors that result in three distinct roots: s equals 0, s equals -2, and s equals -5. On the right-hand side of the equation is the partial fraction expansion, which is the sum of three first-degree transfer functions comprised of constants over each factor. Now we just need to determine what the three constants are. To find C1, multiply f of s by the first factor s. We'll use the factored version of f of s, the middle expression, and the partial fraction expansion version, the right-hand side. Now evaluate at the root, in this case s equals 0. On the right-hand side, only C1 remains. On the left-hand side, we get 3/10 after we substitute s equals 0. So C1 equals 3/10. To find C2, multiply f of s by the second factor, s plus 2. Now evaluate at the root, in this case s equals -2. On the right-hand side, only C2 remains. On the left-hand side, we get -1/6 after we substitute s equals -2. So C2 equals -1/6. To find C3, multiply f of s by the third factor, s plus 5. Now evaluate at that root, in this case s equals -5. On the right-hand side, only C3 remains, and on the left-hand side we get -2/15 after we substitute s equals -5. So C3 equals -2/15. Now that we know all three constants, we can write down the final partial fraction expansion. Since Laplace transforms satisfy the linearity property, I'll factor out the constants. That way, I only need to look for the functions in the square brackets on the Laplace table. Now we'll go to the table to get f of t. We're using the table knowing the Laplace functions and getting the inverse Laplace functions, or the time-based functions. The first Laplace function is 1 over s. The table has capital A over s. In this case, capital A is just 1. The corresponding inverse Laplace transform, or time-based function, is just capital A, or in this case, 1. The other two functions are of the form 1 over s plus little a. The corresponding inverse Laplace transform, or time-based function, is e to the minus at. Recall that Laplace transforms also satisfy the superposition property, so little f of t is the sum of the inverse Laplace transforms of the three functions. We keep the three constants and substitute the three inverse Laplace transforms from the table. Little a is 2 for the second function, and little a is 5 for the third function. We now have the full time-based function of the system, which we could now graph. Again, case 1 is the only case you're responsible for on an exam. Next, we'll examine case 2, which involves a strictly proper transfer function with one or more complex roots. The partial fraction expansion on the right-hand side involves a constant over the real factor plus two constants over the second-degree polynomial that results in a complex conjugate pair of roots. Notice that C2 is multiplied by s in the numerator, so don't forget the s. To determine the three constants, multiply both sides by the full denominator, s plus 1 times s squared plus 2s plus 17. Only the numerator survives on the left-hand side. The right-hand side becomes a new second-degree polynomial. To find the three constants, we'll equate coefficients of each power of s. Start with s squared. On the left-hand side, the coefficient is 5. On the right-hand side, the coefficient is c1 plus c2. Next, we'll look at coefficients of s. On the left-hand side, the coefficient is minus 6. On the right-hand side, the coefficient is 2 times c1 plus c2 plus c3. Finally, we'll look at coefficients of s to the 0 power, in other words, the constants. On the left-hand side, the constant is 21. On the right-hand side, the constant is 17 times c1 plus c3. We now have three equations and three unknowns. Solving these, we get c1 equals 2, c2 equals 3, and c3 equals minus 13. We can now substitute the three constants in the right-hand side. 1 over s plus 1 is on the Laplace table, but the resulting second-degree polynomial is not. Looking at the Laplace transform table, is there a function that's close? The one in the box has the same numerator and a second-degree denominator, but it's in a slightly different form. So let's get the denominator in the form of s plus a quantity squared plus omega squared. Recall completing the square from high school algebra. Any polynomial x squared plus bx plus c can be represented by x plus h quantity squared plus k, where h equals b over 2 and k equals c minus b squared over 4. We have s plus a quantity squared plus omega squared, and we also have x plus h quantity squared plus k. So in other words, little a equals h and omega squared equals k. So that means little a equals 1 and omega equals 4. Now both Laplace functions are on the table. After we get the corresponding inverse Laplace functions, or time-based functions, we get f of t equals 2 times e to the negative t plus e to the negative t times the quantity of 3 cosine 4t minus 4 sine 4t. The last case, case 3, involves strictly proper transfer functions with real repeated roots. The method of multiplying both sides by a factor, then evaluating if the root can only work for one of the repeated roots. We'll need an additional method to handle the remaining repeated roots. The partial fraction expansion is shown on the right-hand side. Notice C1 is over s plus 2 quantity squared, and C2 is over s plus 2. In general, we'll need to determine as many constants in this fashion as the power of the repeated factor. To find C1, multiply both sides by s plus 2 quantity squared. Now evaluate both sides at the root. For this case, s equals minus 2. This results in C1 equaling 12. To find C2, take the derivative on both sides of s plus 2 quantity squared times the function f of s. So in other words, multiply both sides by s plus 2 quantity squared, and then take the derivative of what's remaining. Now evaluate both sides at the root. For this case, s equals minus 2. The result is C2 equals 6. To find C3, simply use the techniques from case 1. Multiply f of s by s plus 1. Now evaluate both sides at the root. For this case, s equals minus 1. This results in C3 equals minus 6. Substitute the three constants and go to the Laplace table as before to determine the full time-based function. For this example, we get f of t equals 12 times t times e to the minus 2t plus 6 times e to the minus 2t minus 6 times e to the minus t. In general, if we had n repeated roots, you would need to take higher order derivatives and then multiply by 1 over k minus 1 factorial. Here's the progression to determine the n constants needed for the n repeated roots. If we add a third repeated root to the previous example, C1 and C2 would be the same. C4 would be C3 from the previous example, and the new C3 would be calculated by doing two derivatives of both sides after multiplying by s plus 2 quantity cubed, along with a 1 over 2 factorial on the outside as shown. In the next section, we'll examine block diagrams and show how to simplify them into various versions, including one version with a single block.